Hello guys, welcome back to another video of Talks Writers, in which we want to discuss and talk about how to post-process the output of physics-informed neural networks. Okay, so the first question is, what is a physics-informed neural network, or PINN? The thing is, I will have some deep videos on this topic to discuss various aspects of this new technology, let's say new progress in the field of numerical methods, which is indeed an overlap of numerical computation and artificial intelligence. But here, what I want to say as a quick introduction to that is, this is indeed a new technique to solve partial differential equations or ordinary differential equations using neural networks. And the idea is, if you can approximate a function using a neural network model like multi-layer perceptron model, which is indeed available for more than 2 decades, and you can differentiate it to the accord based on the input variables, then you can easily represent differential equations using a neural network. And by using that, by defining some loss functions, some functions that you can really train your neural network, you can solve differential equations. So this is indeed the idea. Here I have solved a tissue growth model, indeed a phase field model implemented in these neural networks, inside these physics-informed neural networks, and I want to show you how you can post-process the results. The technology is new, the way that it processes information and helps you to solve the equations is new, and at the same time the output that it generates is a bit different from the outputs that you expect to see. The final output is an animation like this, which is very similar to all the animations that we had till now, especially for the tissue growth. This is indeed the same problem of tissue growth, this time inside a square, inside a rectangular domain. But the cells are seated on the surrounding, and this model tries to predict the tissue growth rate, which I described in the previous videos for the tissue growth project. But the thing is, it has a very fundamental difference to those models, and that's indeed very interesting to learn some stuff about. That you can really learn lots of stuff about ParaView if you just try to follow me and then try to produce this output, this kind of output from the data. And this is indeed a difference, and you can see that instead of having multiple files, each of which are correlated and corresponding for the time steps for single time step, here we have only one file. And the thing is, let me run ParaView and then open this file. Instead of going through this open functional function that I always use, you can easily drag and drop the file into the PyBlock browser, and then I click apply. So the first difference, there is no discretizer space. Here you have only points, because indeed they are the input to the neural network. That's the first difference. And for example, the output of this neural network is the U function, which you saw in the phase field modeling. And yeah, this is the way that it represented, but via a certain number of points and not a grid. That's the first thing. The next thing is, you saw that it was an animation, a time-dependent animation, which means that we had some progress in the evolution of the surface over time. But here you see that there is nothing that I can say, yeah, the play through the time of a click play, nothing happens, because there is nothing here indeed. The difference is, the neural network model looks at t as indeed one of the state variables very similar to, for example, x, y, and z. So t here is not indeed the time step, the different VTK files or VTU files that we already had to act as the time series for ParaView to work. So t is indeed here one of the variables that we can see here in the information panel, that we have ranges for tu, x, and y, and z. It's a 2D animation, so it doesn't have z. But for the t, it varies from 0 to 1, but very similar to the way that x and y are changing. So we should ask ParaView to do something with this t variable. One of the things that I have for myself, this is a technique that I use. I map this t as another axis. This technique works for 2D simulations. Then I ask ParaView to consider this t variable as for example, z-axis. And then I can work with some filters and some animation controls. These are the things that you want to learn here, to change the value of current t, of current time indeed, which will mimic this behavior of this animation control for previous and traditional time dependent problems. So let's go directly to that and let's see how it works. But before that, let me show you how we can, this was in the animation, it was something continuous. You cannot see the points. It was just like normal surfaces that we had before. But here we have points. How to do that? In order to do that, control space, we can use a filter called Delaunay. This filter will connect and interpolate the points to create a surface, to create a continuous surface for us. So there are some parameters. I don't want to change it, and I applied Delaunay filter to this data just as a demonstration. I don't want to apply it right now. I just want you to see the effect of this filter, and you see that it applies, and when you apply it, then it starts to interpolate and create a surface for you. So this is indeed the technique behind creating a surface out of these points. You can apply it to 3D, but it takes lots of time, and also it's not suitable for us. If you consider the z-axis, the t as the z-axis, then you can apply it to 3D, but the Delaunay filter in 3D takes lots of time to complete. So that was indeed the Delaunay filter, but let's go to ask ParaView to consider t as the z-axis. To do that, I use a filter called calculator. Calculator is indeed a very frequently used filter. I haven't used that till now, but I will use it in the future, for example, for fluid flow and also for other types of biodegradation simulations. It creates a new entity, a new variable, based on a calculation of the previous variables. Like if you have the concentration of a chemical species, you can say that, for example, the concentration of hydroxide, you can easily calculate a pH value according to that. Instead of doing that in your simulation code, you can do that here. Everyone knows the formulation, but you don't need to create some extra data to occupy extra space. You do it here, and this is indeed what the calculator filter is intended to do. But how we can use it to create a new axis? That's possible using this checkbox coordinate results. It means that we want to change the coordinate system. We want to introduce a new coordinate system to the program. How to do that? The x values. Let me show you the x values. Indeed, these are the x values. You can see that x varies from 0 to 1, and this is the y values, and they are here as points, as real data. I can use these x values, or simply, because indeed ParaView understands that if there is a variable named x in the data, it means that it's the x coordinate, and that's why I have this to the representation of my data. But you can also use, you can use this x value or the x coordinate. I use x coordinate to say that keep the x coordinate and y coordinate, but add another coordinate system for the z axis. So in order to do that, instead of typing, I just use the mouse button. It's, I think, visually is more, I think, convenient for you to see. So x coordinates multiplied by I hat. I hat is I hat, j hat, and k hat, or indeed the unit vectors of this 3D Euclidean space for us. I say x coordinate multiplied by I hat means that the coordinate system for the components in the x-axis, the coordinates along x-axis are the ones that I intended to use, which means literally don't change it, because x coordinates by I hat means that the x coordinate should still be there, plus coordinates y multiplied by j hat, and it means that please don't touch y coordinate, it should be the same. But here comes the technique, plus t multiplied by the k hat. So I ask ParaView, please consider t as my new z-axis. I press apply, nothing happened. No, of course something has happened. The thing is, I need to change to 3D, this bottom, 3D indeed representation, 3D view. And then here is what I expected to have. The representation of u, and you can see that the neural network has indeed modeled something for me. And this is indeed the base, the 0 of the z-axis, and here is the top surface, which is indeed 1 for me. So, and I can see that, yeah, there are 10 divided subspaces for the t, but I can also see that from another way. I can divide my viewport into spreadsheet view. For this value, I can just observe that t is 0, then it goes to, for example, 0.1 and so on, 0.2 and 3 and 4 by till 1. So I know that I have indeed 11 steps from 0 to indeed 1, each 1/10. So in order to capture only one of these surfaces, only one of these floors, I can use the threshold filter. What it does, you can specify the threshold. It's very similar to clip clip by scalar, but here you specify two thresholds, one upper, one minimum, and one maximum. For example, imagine that I want to post process the value at 0.5. In order to do that, I can go, for example, 100ths below and 100th above, which means that 0.49 and 0.51. And then I click apply, and then I have only that specific value of t. And you see that the scalars is selected as a t. It was the first one. I forgot to change it, but luckily it was the one that I wanted. So I can switch back to a 2D view. First I have to adjust the camera. It should be this one. And then I switch to 2D. It's much easier. So that's it. But how to create an animation out of it? This is another interesting thing to learn, which is indeed animation view. The animation view panel helps you to have full control of what's happening on the animation. There are lots of things to specify here. You can, for example, cut some of the frames that you don't want. You remember in one of the save viability videos, I told you that you can cut part of the frames, but it is relatively something advanced, and I will show you in the future. This is indeed a place. This is where you can cut some of the videos. This is very similar to the software programs that allows you to have control on the animation on a timeline basis. This is indeed the timeline of ParaView. Let's define first the time concepts for ParaView. We can say that the start time is 0 and time is 1, and we have 11 frames, not 10 frames. I click apply, then it creates this, and here we want to say that on each frame, now you can see that I can go on, but nothing is changing indeed. On each frame, try to change the threshold of the lower and upper bound of the threshold, of this threshold filter. In order to do that, I use this add new item bottom. So I say that for the threshold range 0 and threshold range 1. Still nothing changes. I need to, it goes to the 0, but I need to change both values. The thing is, I told you 100 below and 100 above. For the lower bound, so 100 below of 0 is, this is negative, and for the 1, it becomes this one. And ramp interpolation is automatically applied, and for this one, 100 above and 100 above for 1. So in each frame, I'm indeed modifying the properties of a filter. This is very useful. If you use it, for example, you can use it for lots of things. You can imagine yourself now, you know ParaView. You can work with this panel to change the properties of filters over time. It can be a clip, it can be a contour, in this case it's a threshold, or you can orbit the camera, lots of stuff. So here the thing, and yeah, I zoom out, and then yeah, that is indeed moving. So what I need here is adding another filter to this pipeline, which is indeed the Delaunay. Yeah, that's what I want, that I apply the Delaunay to the output of threshold, which is indeed controlled by the time, by this animation view of the timeline of ParaView. So this is indeed the surface, you can see, and if I go through the animation, I see that, yeah, it's moving. And yeah, that's the data range is not correct, but I don't care about it, because what I want to apply is indeed another filter. I want to apply another filter, another clip filter that removes the part that U is, I don't know, maybe I should invert it. Yeah, that U is below 0 or above 0 in this case. So that's it, and then I convert the variable to solid color. I don't want any variable to be presented in the animation, and then that's it. That's what we intended to create. That is very beautiful, because now you know that the path that we took to reach this. We applied a calculator to create the t, to ask ParaView to consider t as a z-axis, then apply the threshold, and we control the threshold through this artificial time. This is indeed artificial time, because we know that time is indeed in the z-axis. We just want to apply threshold to that, and through artificial time control the threshold, and then a Delaunay, and then a clip. And then you can export the animation and have this beautiful animation. This is indeed, yeah, this is not beautiful, but the technical aspects behind it indeed make it beautiful, I think. So that's it. I hope you enjoy that. I really enjoy that. I hope it's the same for you. Try to reproduce it with the data that you can find. I told you before, you can find the data in the description below, and download the dataset and try to reproduce the video. So have fun, and see you later.